Alright, I'm going to be going over how to do this topic on ALEKS. So first thing you do is circle everything they give you. Right here, they said 152.1 milliliters of a 0.4 molar solution butanoic acid, 0.5 molar NaOH. Butanoic acid pK is 4.82, and you're adding 131.6 milliliters of NaOH. Just to make things easier, just calculate the total milliliters of solution. So you had 152.1 milliliters to begin with, and then you added 131.6 milliliters. So off to the side somewhere, I'd put 152.1 milliliters plus 131.6 milliliters, 283.7. Right, now that we have that, the actual question requires you to find the moles of butanoic acid and the moles of NaOH, because you got to remember that whenever you have a strong base and a weak acid, they react until one reactant is used up completely. So you got to know the amount of each to find out which one gets used up and which one stays after. And to do that, you have to remember this equation right here: molarity equals moles over liters. And we're finding moles. All we do is multiply moles times liters, or not moles times molarity times liters. So moles equals molarity times liter. Everything I circled has the information about your compounds. So I'm just going to abbreviate butanoic acid as BA. So for that, you have 0.1521 liters. To get milliliters, to get liters from milliliters, all you do is move the decimal over 3 places. So 1, 2, 3, that's 3 places, and that's how you get liters. And then you multiply by 0.4000 molar. And then for NaOH, you do 0.1316 times 0.500. And when you calculate that, 0.06084 moles of B8, and you get 0.0658 moles in NaOH. And then you gotta write the reaction. As I said before, when you have a strong base in the presence of a weak acid, they react until one reactant is completely used up. So you have, I'm just gonna write it so you can understand. So initially you had butanoic acid, which is HC3H7CO2, and then you added NaOH. And this goes until completion to produce water and the conjugate base of the weak acid. So C3H7 CO2 minus. The conjugate base is just this acid without its proton, because the proton gets neutralized by this OH. So after you have the equation, you gotta look at the amounts of reactants you have. So from here, BA is this is BA, butanoic acid. You have 0.06084 moles of BA, and you have 0.0658 moles of NaOH. So you gotta look at these numbers and figure out which one you have more of. So right here, you have 0.0658. To make it easier, just pretend you don't have this decimal right here. So if you pretend you don't have the decimal, you have 658 or 6,580 to make them have the same amount of digits, and you have versus 6,084. 6,580 is bigger than 6,084, so you're going to have this in excess. And all of this is going to get used up to produce the conjugate base. So when this reaction goes to completion, this gets used up, converted to this 0.06084 moles. And to find out how much excess NaOH you have to subtract the amount of NaOH you had at the beginning from the amount that reacted with this weak acid. So in the beginning you had when you added, you had 0.06580 moles of NaOH, and then it reacted with butanoic acid, and this much of it reacted with butanoic acid. So 0.06084 moles. And that would give you 0.00496 moles NaOH. Now, once you get to this point, you have to consider what's in your solution, or your beaker, or whatever. So this is a beaker. And in this, when you added NaOH to this butanoic acid, you had excess NaOH, and all of this got used up and got turned into this conjugate base. So you have NaOH, and then you have this conjugate weak base of butanoic acid, and you have C3H7. So when determining pH, you gotta look at the species you have and determine if any of them are strong. Right here, this is a strong base. So anything this does overwhelms this weak base right here. So no matter how much of this weak base you have, well, it won't matter how much of this weak base you have, because this strong base is going to dominate pH since it's way stronger than this weak base. So all you have to consider is the amount of NaOH you have. When NaOH is in solution, it dissociates into Na plus and OH minus. To find pH, there's two ways you can do it. First, you can find pOH and then subtract pOH from pH. Or you could find, sorry, I had to think for a moment there. You can either use this right here, or you can use this right here. I like to use this one because it's much easier. You don't have to deal with powers of 10, but you can do it this way if you know how to. So first I find the pOH. However much NaOH you have, it gets dissociated into OH minus. So you have 0.00496 moles of NaOH, and you'll have 0.00496 moles of OH minus. Now to find pOH, pOH is equal to the negative log of the OH minus concentration. And you have OH minus, but it's in moles, and you need to convert it to molarity, because that's what concentration is in. That's the unit concentration is in. So to do that, you can go back to this equation here. You have this much 0.00496 moles of OH minus over the total liters of solution. And this, we did that in the beginning over here to make things easier. So this right here is the total milliliters of solution, because at first you had 152.1 and then you had 131.6. So you need liters. Again, I just move over the decimal place 3 places. So it's 0.283.7, or not 0.7 because I moved the decimal. And I got from here I got 0.01748 molar OH mass. And remember, we're trying to find, the end goal is to try to find pH. So to do that, first you got to find pOH. So, or you can do this way again. pOH equals negative log of this, what we found out is 0.01748. So pOH turns out to be 1.7573. And to find pH, you just rearrange this equation, and it turns out to be pH equals 14 minus pOH. So to find pOH, you just subtract this from 14. 14 minus 1.7573 equals 12.24. And that's going to be your final answer. Let me try that right now. So as you can see, it's right. And there's one more type of problem with these. The first one we did right now was that, okay, so when you do this reaction with a strong base and some weak acid and it goes to completion, there's cases where you have this has excess, the NaOH, in which case you ignore whatever conjugate base is produced. But then you also have cases where you have extra weak acid, so you have excess weak acid, then you have to consider your conjugate base, and you don't ignore it, you gotta use isolables. I'm gonna try to find a question that has that to try to solve it. All right, so it turns out, luckily, this question is one of those questions where you have excess weak acid instead of excess strong base. So again, the beginning is the same process. Well, what I like to do is just circle everything I have. 211.4 of 0.72 hydrozoic acid, 1.1 molar of KOH, pK of hydrozoic is 4.72, and you're adding 53.36 molars of potassium hydroxide. Again, first thing I like to do off the side is find my total milliliters of solution, because we need to use that again. So off to the side here, 21 to 11.4 plus 53.36, and you get 264.76 milliliters, and you just keep that there. So the beginning is still the same process where you got to find moles. I'm just going to abbreviate this as HA, hydrozoic acid, to make it easier. So first you find moles of each, the strong base and the weak acid. For HA, it would be 0.2114 liters. Again, I'm just moving the decimal over 3 places to convert from milliliters to liters. And then for potassium hydroxide, it's decimal over 3 places, which is, when you have 2 digits, you got to remember it's 3 places, not 2. Don't just move it over to the first digit. So right here, it's 0.05336 liters with 1.1 molar, 1.1 molar. And let me just do that. So this right here would be 0.15228 moles of HA. And this right here would be 0.058696 moles of KOH. Now, where it differs from the last question is in this reaction right here. So when you do HA plus KOH to produce H2O plus A minus, and you consider the moles of HA and the moles of KOH, you have more moles of HA. So this is going to be the thing that's going to be used up all the way, and this is going to be left in excess. So if you do this, 0.15208.0586696, since this is a limited reagent, you're only going to get this amount of conjugate base, because you can't react any more than this with a acid. So this is going to get completely used up, and it's all going to convert to A minus. So you get rid of the KOH, and you get 0.058696 moles of A minus. And then remember, you also use up some weak acid when you react this KOH, and to find how much you have left after that. So to find how much you have in excess, you do this amount minus how much you reacted, which would be with the KOH. So 0.152208 minus 0.058696. And that would be 0.0512 moles of HA. So at this point, you have to do an ice table. So I just like to convert my moles to molarity, because it makes it easier at the end, so you don't have to do it at the end. I think that's the right way to do it anyways, where you have an ice table with molarity. So to convert this to molarity, you do this equation right here. Moles over liters, you have moles, and this is your total solution. So again, I'm just going to move the decimal over 3 places to convert milliliters into liters. 0.264.76, and you get 0.353195 molar HA. And I also like to convert this. You have to convert this to molarity too. And again, the liters is the same for both of these because they're both in the same solution, and you're adding the initial solution, not concentration, the amount of the initial solution to the amount of the KOH you added to it. So this would be the total volume. And once you do that, hold on, 0.26476, you get 0.221695 molar A minus. Now, like I said, it gets more complicated here because instead of having your KO or strong base in excess, you have a weak acid in excess. So essentially, this makes a buffer. And to find the pH of a buffer, you got to do an ice table. So the general equation would be HA. Hold on. HA goes in equilibrium with H plus and A minus. So the initial HA would be right here, what you got from the excess remaining from this first reaction that happened. So this is step one. This right here, the ice table, is step two. So first this reaction happens, and then you get a buffer from the weak acid with a conjugate weak base. So first this happens, and then this happens. And from this first equation, you have this much left over. So this would be your initial for HA. I'm just going to shorten the amount of digits so it can fit. So I'm just going to put 0.35 molar. But in the calculator, I'm going to use all digits. So make sure to use all the digits in your calculator too until the end where you got to round to 2 decimals. So that's the initial HA. You don't have any initial H plus because it hasn't reacted yet or gone to equilibrium yet. And your initial A minus is the amount that was produced in this reaction from the KOH. So you know how this got used up and then all of it went into A minus? That would be your initial A minus, which is right here. So 0.22 molar. And the change here, since there's more of this is going to get used up to produce that. So this would be minus X. That would be plus X. This would also be plus X. So by the end, you'd have, and just like all the other ice tables, you need a Ka. And you might think that they didn't give it to you, but here they gave you pK. pK is just the negative log of the Ka. So to go in reverse, Ka would be 10 to the negative pK. So when you write your equilibrium equation for this, it'd be this. It'd be H plus times A minus over HA equals Ka, which is equal to 10 to the negative PA, which is equal to 10 to the negative 4.72 from this right here. So after you do that, you take this and you fill in these values for that. So you have 0.22 plus X as A minus, X as H plus. So the numerator would be X times 0.22 plus X. The denominator would be 0.35 minus X equal to the Ka, which I found in the calculator by doing 10 to the negative 4.75. The Ka is 1.905 times 10 to the negative 5. And you got to figure out whether you can make the X a small approximation or not. And the way ALEKS does it is they take the Ka and then they subtract this bottom concentration right here. So oh no, it's the other way around. So they take this bottom concentration right here and then they subtract this thing right here, the Ka. Let me do that. So when you do that, you get 0.349, which is really close to 0.35. So you can like round it up. So you can assume that X is small because it doesn't really change much from the initial concentration. Say you subtracted something from 0.35 that was like a Ka of 10 to the negative 2. If you subtracted that, this number would change a lot more. But since it doesn't, you can assume that X is small. So right here, you get rid of minus X and you get rid of plus X. And you're left to deal with 0.22X over 0.35 times the Ka, or equals the Ka. So if you do the math, it'd come out to 1.905 times 10 to the negative 5 times 0.35 equals 0.22x. And to find x, you divide this right here by 0.22. X equals 3.031 times 10 to the negative 5. And you have to remember what this x means. This x right here was the amount that was taken away from the HA and the amount of hydrogen, or H plus, that was produced. And to find pH, you got to deal with, well, this is a buffer. So the first thing, to find the pH of a buffer, you got to use this equation right here, the HH, Henderson-Hasselbalch equation, which is pH equals pK plus log of A minus over HA. So you fill in all your values. So pK you have here is 4.72. And at equilibrium, your A minus would be 0.22 plus X. And what you found here was X. So you do 0.22 plus 3.03 times 10 to the fifth, or 10 to the negative fifth, over, and your HA right here was 0.35 minus X. So 0.35 minus this 3.03 times 10 to the negative fifth. And then once you compute this, you should get the answer. So let me do that. And the answer I got was 4.518. And asked to round to 2 decimals, so it'd be 4.52. And let's check that. So I think it's right. And you'll only get those two types of questions where you either have excess KOH or excess weak acid, or not excess KOH, excess strong base, or excess strong, not strong, weak acid. So the first one, okay, the first part of this video, let me read it out. First part equals excess strong base. And the second part of this video, excess weak acid. And to find what you have in excess, you remember you gotta do the equation of the weak acid plus the strong base into H2O plus the conjugate of this. And you gotta consider the moles of this and the moles of this. Whichever one you have more of is gonna be the excess. So say you had 3 moles of HA and 5 moles of strong base. Since you have more moles of strong base is gonna be excess, and you go to the first part of the video. If you have the other way around, what you have, If you have 5 moles of HA and 3 moles of SB, you have excess weak acid. So you go to the second part of the video, or the second question I did. I hope that helps.